So let's pick up where we left off there. One last thing I want to mention about values for static and kinetic coefficients of friction. These will often be reported in ranges. So again, if you just go out and look up coefficient of friction for stainless steel on aluminum or something like that, which you don't do that, they tend to corrode each other, but it would give a range of values, and often they're less than 1, but they don't necessarily have to be. Okay, all right, so that's a good amount of theory. Let's talk applying it just a bit to friction reactions we might encounter. And I normally just classify them two ways. One is basically the large contact area, and that's the idea of the big box that we just saw a little bit ago. Right, I've got a large contact area on some sort of a rough surface. When I draw this in a free body diagram, you're going to have a normal force. You're also going to have your friction force, assuming if I'm applying some force P on it here. Right, P, weight. You're going to have a normal force. There's going to be some distance x from the center. Your normal force. And so, and basically your value of x is going to determine whether this thing tips over or not. The other type that we can see is what is normally pretty common for us is going to be point or small contact. And so if this is the case, then we're not so much worried about is it tipping or not. It's more of a kind of like a rocker or a roller or just a simple point. You're going to have a normal force. It's going to be perpendicular. The normal force is normal. It's perpendicular or normal to whatever surface is applying it. And then what's new then, of course, is the friction force. And the friction force, it's determined as, is this going to slide this way? If it's going to slide to the right along this surface, then the friction is going to apply a force to the left. On the other hand, if maybe something is pushing it from up above and it's pushing it out and it's trying to slide out this way, if that's the tendency is for this thing to slide to the left, then the friction is actually going to push opposite of that. It's going to push back to the right. So I've drawn it to the left. That doesn't mean it's always to the left. Here's where you have to start thinking like an engineer and not so much just, well, this do that. You have to actually look at it and say, well, if I apply forces to this thing, how is this thing going to move based on the forces applied? I need to draw friction opposite of that sliding motion. Okay. So really it just kind of depends on, do I need to worry about this x value? Can this thing tip over? And so is there an x value that doesn't make sense? Lecture 16, this is going to be page 3 of something. So common situations we might encounter in this class concerning friction. Situation number 1, the object cannot move. The object cannot move. Simply saying the load is too small. So if I've got this box here and I apply a force P to it and I don't apply enough P to cause this thing to start sliding, well, what that tells me then is that the friction force is going to be less than, or at most, well, let's just say less than. The friction force is going to be less than mu sub s in the coefficient of static friction multiplied by the normal force is going to give you the limit of the friction force. If I've not applied enough force to overcome this amount of friction force, the friction force is going to be less than. Don't just set your friction force equal to this value. You're looking for very specific words to tell you that these are actually equal to each other, right? Now, the second scenario, right? And so in this scenario, F and N must be found independently. And through equilibrium equations. The second scenario we might encounter is the object just starts to slide. The object is just starting to slide. We call this impending motion. The motion is impending. It's just about to happen. Right as it's just about to start sliding, that's when this friction is equal to its maximum value. We can set it equal to mu sub s times n. So this is the only time I can say F is equal to mu sub s n, is if I know somehow impending motion. They might say, find the maximum force can be applied, or something like that. That doesn't mean it's a good chance we're going to be able to say this, although it's possible the thing can tip over. That's a way that it can move, right? But that's a common thing we might encounter. If they somehow have described to you right at the point where it's starting to slide, or what is the minimum requirement, or maximum allowed, or something like that. Right. 3. The object is sliding. If they've made it very clear the object is sliding, or somehow you've determined that you don't have, your friction doesn't reach this amount, your friction exceeds this amount in order to stay static, well, that means it's no longer static. Now it's moving. Once it's sliding, now your friction is equal to mu sub k times n. And I don't assign anything involving sliding once it's already moving. Normally I'm only focused on stuff of, hey, what is the amount of force right at the point it starts to slide, or what's the, what is the minimum amount of force required to stop it, or something like that. Here in this case, we're talking about, well, it's actually moving. Once it's moving, this becomes your friction force. It's a simple equal to. The fourth common situation we can encounter, we've alluded to a little bit. Object is tipping. Say tipping over, or beginning to rotate. Right? So here's the thing, in this situation, we don't know if the friction force has reached its maximum. It may not have. We can only find F and N with equilibrium. Use sum of moment equals 0 to find the x, basically. Right? And again, we're talking about this situation back here. We're saying, hey, make sure you use your sum of moments and figure out, is this x value so large that it puts the normal force outside the box in order to satisfy sum of moments equal to 0, because that can't physically happen. The farthest it can go is to either edge. So there's that x value has a limit. If you've exceeded that limit, then it's tipping. Right? Just like friction has a limit. If you exceeded, friction can go all the way up to mu sub s n. That's its maximum value. If you need more than that to keep it static, well, then most likely it's sliding, and now the friction force is equal to mu kn. So there's two types of motion. Is it sliding? Are the two surfaces sliding relative to each other? Or are the two surfaces, have you applied so much friction at such a height that, or so much force at such a height that now the box is tipping over because it has enough friction to keep it from sliding, but there's not enough weight distribution to keep it from tipping over. Okay, so those are the four types of scenarios we can encounter. The two types of reactions that we can encounter involving friction, and basically it's just the presence of the ability for the thing to tip over. Something like this is not going to tip over, it's just going to slide based on what we have there. Okay. All right, I'm going to stop us there and start the next video. Let's start looking at some examples. I got several examples we want to look at.